So thank you very much for this very good introduction, and I prefer to stand up instead of sitting in the car coming from Rome. European Space Agency. I'm the director for Earth observation. Earth observation is really those satellites that look from space down to Earth and measure different parameters of our planet, and to see which parameters and what the measures are and how our planet is changing. So allow me to show you a few slides, but also I would like to have an interaction and discussion afterwards, if that is possible. And I'm really glad to be here in Foligno. It's a beautiful place, and I would like to explore it later tonight. I think I've heard it's a very beautiful town, and I'm really looking forward to be here. But also, I find this a very nice opportunity to have this type of seminar and this type of colloquium, because this, I think, is very important to have these activities not only in the capital in Rome or in Milano or in Frankfurt, but also in smaller towns like Foligno. And I'm very happy to see that there's a very active science community and a very active science dialogue, which is really fantastic. And especially for the young people, I hope to give some information and hopefully also some inspiration. Okay, let me show you what is the European Space Agency. This shows just one paragraph, one article of what the European Space Agency is, or who we are. We are, as you see here, created in 1975 in order to develop space research for exclusively peaceful purposes. That means we are working for civilian applications and not for defense, not for the military, but for civilian applications, to really see from all aspects of space of what we can do and what the various space activities are. I want to show you this slide here, which is showing the member states of ESA. The European Space Agency has 22 member states. They are not exactly the same as the European Union. As you know, the European Union has 28 member states still. The UK is on its way out, or maybe not. But the ESA member states are mostly overlapping with those of the European Union, but not all of them are the same. As we say, we have 22. Most of them, as you see here, are the same ones. There are two member states which are not members of the European Union, which is Switzerland and Norway, which are not members of the European Union but members of ESA. But there are other member states of the European Union which are not members of the European Space Agency. Those are mostly the smaller Baltic countries, Malta, Cyprus, for example, because they have no space activity and therefore they are not a member of the European Space Agency. The UK, of course, is also a member state of ESA, and after the UK is leaving the European Union, after Brexit is implemented, they will still remain a member state of ESA, but not a member state of the European Union. Another country which you see here is Canada. Canada is an associated member of ESA. We have a long-term membership agreement or cooperation agreement. They are not a full member, but a cooperative member, as we call it. That means that they are cooperating on many projects, but not having all the full rights of voting, for example, like other member states like Italy or other countries. This is the budget of ESA, and it also shows a little bit what activities we are doing and where we spend our money. As you see, all together, this is for this year, 2019, we have 5.7 billion euros. ESA is therefore the largest research organization in Europe in terms of money and money we are spending. You see here the various activities in which domains this money is spent. Navigation, 13%. Space transportation, that means launchers, rockets. Then we have here Earth observation. This is my budget in my directorate, 24.3%. It's roughly 1.5 billion euros per year, which I'm spending in my directorate mostly to buy satellites, to develop satellites, but also to do a lot of research and the use of these data in order to convert data into information which is relevant to people. You also see other domains like space situational awareness. You see technology support, telecommunication, telecom satellites, and integrated applications. Human space flight, this is astronauts. We are working with the Americans, with NASA, on the space station, and we provide also regular activities on the space station. So you see there's a full portfolio of activities which we are doing in ESA. Actually, next to NASA, next to the Russian Space Agency, we are one of the very few agencies who is doing all the space activities, from planetary research to astronauts, to rockets, to Earth observation, to navigation. So we really have a full portfolio of all the space activities worldwide. So this is the side of the money, which is the way it is spent, this 5.7 billion. The way we get the money is through contributions by ESA member states. About 20% of our budget is a mandatory program. That means every member state of ESA, according to its GNP, is providing about 20% of our budget. But 80% of the budget is competitive, or we call it optional programs. That means that we are putting proposals on the table. We are inviting member states to subscribe. We put larger programs together. Let me take the example of space transportation. We have a rocket, Ariane, as you know from the news. Ariane 5 is our current rocket. We are developing a new one called Ariane 6. And this new rocket, we are putting the program together. We propose to member states, this costs so many millions or billions of euros, and who wants to participate? And then member states put money into the pot and they participate in the program. There's one golden rule in the participation of ESA programs, and this golden rule is that if you put 100 units in, say 100 million euros into the pot, you are guaranteed to get at least 90 million back into the country in the form of industrial contracts in the country which is contributing. So the governments are putting money into ESA, and we, ESA, we manage space programs, and we have competitive tenders. That means competition for satellites and rockets, but this work is done in the member states. In fact, it is 85% of the money which goes back to member states, and 15% is used for our salary, for the buildings, for the test facilities, for the research facilities, for antennas, all the activities which we are doing. Next slide shows Earth observation. So this is now breaking down to the budget which I'm looking after, which is the Earth observation activity. And there our slogan is that we are taking the pulse of our planet. So we really measure our planet, the various parameters of our planet from different sides, different elements of our planet. The atmosphere, the oceans, the land surface, the cryosphere, the various parts of our planet, and really see how the Earth as a system works together, and how the Earth as a system is changing, also including climate change, which is of course a very important parameter. What you see here are some of the globes or some of the measurements we are taking with our satellites on a routine basis, on a daily basis, to make sure that we really capture very well and we understand well how our planet works and how our planet changes. I just want to welcome my little daughter, who is here with my wife, which is a very young, interested scientist who is coming as well, and they just sneaked in. Okay. Going back to the Earth observation program of ESA, what you see here is there are 3 lines of activities or satellites which we are developing. We call them the Earth Explorer missions, which are addressing science questions. Then we have one line of satellites called the Copernicus satellites. We call them Sentinel satellites. Sentinel, like the guardian of our planet. And then we have one line of satellites for metrology, which you see here in the orange color. The first one, the green one for science, are satellites where we ask the best scientists in Europe, what are the questions in Earth observation in order to better understand our planet, which you need to have answered. And they tell us better measure ice melting or wind in cloud-free atmosphere or the change of climate or the carbon dioxide concentration in the atmosphere. So whatever they tell us as the important parameters, we then take it on board and we develop satellites that measure these parameters. And these satellites which are measuring these parameters are using the best technology existing, and in many cases, I would say in almost all cases, this technology does not exist before, and we develop completely new methods and technologies from space in order to measure these parameters which the scientists are asking us to address. So this is the green line, which is the science missions, or we call them the Earth explorers. Then we have this blue arc here, which is the Sentinel Missions, which are part of the Copernicus program. Copernicus is a new program, which is, well, new is in space terms, new means 20 years old, which was developed to really establish a large fleet of satellites to monitor in a routine basis, in an operational way, various parameters of our planet for agriculture, for disaster monitoring, for ship routing, for fire brigades, people to know where the fire is, and many disciplines which can be measured. And this is a fully operational system. That means we are making frequent measurements reliably to the citizens in order to provide this data. And then we have the Metrology Satellites. Actually, this is our oldest line. This goes back to 1978. The Geostationary Satellites from 36,000 kilometers orbit are measuring on a routine basis our state of our weather. And we have other satellites underneath that are circling around the Earth. They are not geostationary, but circling around the Earth. We call them polar orbiting satellites, which are complementing these geostationary measurements, again, for weather forecast and for daily weather forecasts. About 80% of today's weather forecast information comes from satellites, because satellites can cover all the parts of our planet and really monitor all the parameters and all the elements of our planet. And here, really to highlight that this whole portfolio of all these satellites, science, Copernicus, and metrology, together, we have 15 satellites in operation, 25 under development, and 12 in preparation. And this is by far the biggest portfolio of satellites we have ever, but also this is, and you may not believe, the largest Earth observation program in the world. So Europe has really established a leadership in Earth observation worldwide. And if you compare these assets with the US or with China, we have the best system in the world. Europe has a leadership in Earth observation. And I'm really saying that because quite often you read in the newspaper about, or in TV about SpaceX just having launched another rocket. Falcon Heavy was launched yesterday. The most recent launch of Falcon Heavy with the car on top, which was flying to outer space, was very remarkable. So America was launching with Falcon Heavy the first rocket of this type, which can land again on the Earth's surface, which is quite a remarkable technology. And America really has taken leadership in the launcher program. On the other side, you hear that China is developing a very strong launcher program, but also they are landing on the backside of the moon, which happened about a month, 2 months ago. Again, this is quite revolutionary, it's quite good, but also China is building up a space station, in addition to the existing space station, but they will build their own space station. So again, you hear that China is leading in space and is doing quite remarkable things. And then people say, what is Europe doing? Where is Europe leading? And this domain in Earth observation is one where Europe has leadership and where we have the best Earth observation program in the world. This shows the quality of the measurements coming from satellites for metrology. And what you see here is that the measurements, which are taken here in different colors, the orange part of this circle is measurements taken by in situ measures, in situ devices. That means temperature measurements by a thermometer, wind measurements on ground, radiosonde measurements, which are radiosondes going into the atmosphere. So these are measurements taken basically on the ground with these weather stations. So only this part here is data coming from typical weather stations. Of course, 50 years ago, this orange was covering everything because there was no satellites. But today, satellites are taking more and more of these parameters or these observations for daily weather forecast. And the yellow one is the European one. It's called METOP, which we built, and we just launched the last one of this series of METOP last year. As you see, this yellow arc is providing the largest contribution to the accuracy of daily weather forecast. So in other terms, or in simple terms, satellites are essential for daily weather forecast, and European ones are contributing most of this information for daily weather forecast for tomorrow, the day after, or up to about 10 days and beyond. This is one slide which looks a bit busy, maybe confusing, but what I'm showing here is a pictogram of different satellites, our science missions. They are with these names here, Gorgeous, Moss, Cryosat, and so on, which are flying. And these are the future ones that are flying, that are developed right now and will be flying in a couple of years. Again, this is part of these science missions, these Earth explorers I mentioned before. These Earth explorers really provide science, and you see here we have about 4,700 scientists across Europe, or some of them even outside Europe, which are working with these satellites, which are producing information and science based on these satellites. And we have about 300 publications per year. That means one publication every day on average, which is produced from these satellites. This is, as I said before, high risks for great rewards. The technology is risky. Sometimes we're getting stuck because it is new technology, and we are seeing technological hurdles, and we cannot further develop because something doesn't work. So we have to see what we do in order to proceed. Just maybe one example. AELOS was the last one we launched here. As the name indicated, is measuring wind. It's a very, very fantastic satellite, but the technology, which is a laser on board a satellite operating in the ultraviolet part of the spectrum, has never flown before and is very, very complicated to do. It took us 11 years extra compared to the original launch date to master the technology and to be able to launch the satellite finally last year. 11 years delay of this satellite, which shows also how complicated these satellites are and how many people are working on it and how challenging the technology is. In fact, we have been asking NASA for help, whether they could tell us some of the problems which we encountered and how to solve them. And NASA said, no, sorry, we don't know. We have tried twice, and they have failed twice. They have launched 2 satellites with such an instrument on board, and it did not work. One worked only 52 hours, the other one didn't work at all. And they said, if you find out how it works, please tell us, because this is very interesting, and we want to know as well. So this is really technology that is complicated, is very difficult, and we are working with our engineers across Europe, with industry, obviously, and our own engineers to solve these problems. This is one example, just to highlight some of these science and these examples which we are having. This is the Earth core, which is measured with one of our satellites called SWARM. And what we discovered is that this jet stream, which is the flow of this iron inside the Earth, has been speeding up. We say it's going fast. We call it a jet stream. In fact, it is not so fast. It is 40 kilometers per year, but it used to be much slower in the past. But we measure now that this is really accelerating, and we don't know what that means. This is something that our scientists are still trying to understand. One thing that this increase of the speed of the iron core is connected to is our magnetic field. And we also know that our magnetic North Pole is moving, and is moving from Canada towards Siberia. And is moving faster, again connected to this speed which has been increasing. And what might happen, what our scientists are expecting, is that the North Pole may flip to the south. And the North Pole may be in the south in some time. We expect this to be not before 100,000 years. but 100,000 years in the geological terms is very short, and this will most likely happen or could happen. In fact, the pole was already flipped once in the past, we know that, and this could happen now again, and this is something which we are measuring with this satellite. Just another example, and this shows a bit how many publications we are having or we are creating from these satellites. I'm not going into the various details of these colors, but just to show that these are the publications based on the Scopus database, so that means scientific publications, and they are increasing using our data. You see here is 1,400, roughly as a figure. That means 2 to 3 publications per day based on this satellite data, and this keeps increasing pretty fast because new satellites come on board and new science is being discovered. This line here is another pictogram. This shows the Copernicus missions, so these operational type of missions I explained before. Copernicus, obviously, very disruptive, revolutionary at the time, but also in the space sense, the Copernicus program was really disrupting the way Earth observation satellites have been conceived in the past. What we do here is, for the first time, have a long time series of a fully operational system with many satellites which are being developed. There are 6 families which are existing today, Sentinels 1 to 6. Some of them are launched, some of them not yet. Altogether, there's a set of 20 which we are launching here, which is addressing all these various aspects of our climate system. But I think I want to point out one figure here, which is this one, 150 terabytes of satellite data per day. Every day, we are disseminating from our central data hub 150 terabytes. And this is the largest amount of satellite data worldwide, and we are serving the community worldwide with this data. And the best is that these data are full, free, and open. So everyone, you can log on our computer, select an area of your house, of Foligno or any other area, and you can download these satellite images for free every day. And this is something that really we do in order to create science, but also make this space investment available for people for benefits of every single citizen which may benefit from this. And these are some of the examples of this satellite data. This is obviously well known, Etna, which is erupting frequently. What you see here is one of the eruptions. This is a lava stream that came out while the satellite was flying over. Quite impressive, and you can these images on a regular basis in this case with our Sentinel 2A. There's a statement here from BBC World News that this is quite an interesting application for regular monitoring of volcanoes as one example, but we are using it for many applications. Another example, also not too far away from here, is the earthquake which happened in 2016 here close to Castelluccio. And what you see is, again, one of these Sentinel measurements, and what happened after the earthquake in terms of how the Earth changed. What you see is the red area here and the blue areas. So the red area is areas which have been going down by 30 to 40 centimeters. So the area around Castelluccio has been sinking in after the earthquake. And the area around Monte Gallo has been rising as a consequence of the earthquake by another about up to 30 centimeters. So you really see that the territory has been changing, one part going up, one part going down. This is the result of the earthquake, which we measured after the earthquake, comparing images from before the earthquake. And the accuracy of these measurements is in the order of millimeters. So we can see changes in the order of millimeters. And this is something also very interesting in Italy in particular. Infrastructure, schools, bridges, you can imagine, if you can monitor them regularly and see how they change, and if there is a change of 1 millimeter, 2 millimeters, before they might collapse or before a problem might occur. This is something that Italy wants to build up now as an operational service. It already exists in Norway. Norway has done it for the whole country, to monitor the whole country and see what changes are occurring. And one of the next countries is Italy, which wants to build up a national system to monitor changes of infrastructure, in particular schools, bridges, and others, for early warning of some problems that might occur. Snow extent, another example, of course, extremely important for climate monitoring and changes of the surface. This is my little girl called Stella, is now assisting in the presentation. And so this is something that is obviously important to understand changes of snow cover, but also its effect on radiation and how this impacts the climate and the changes of the climate system. The next example is pollution. Again, we have a satellite that called Sentinel 5B that monitors different trace house gases, different gases in the atmosphere. In this case, you see NO2, which is an indicator or which is produced by traffic and industry. So it's very clearly linked to pollution by people. And you can also immediately recognize the centers of pollution. Of course, in Italy, you see the center here around Milan, Torino, the Po Valley, Rome, Napoli. The rest of Italy is pretty clean. That means green and blue colors. But then in Europe, you also see the huge centers of pollution around London and the middle part of the UK. Then Belgium, Netherlands, Germany, the Ruhr Valley. This is Paris, Madrid, Barcelona, Moscow. So you immediately see the big centers of people also connected to big pollution. But it's quite interesting to see. This is an image which is an average of between April to September. But you can get these images every day, and then you can really see how the pollution is propagating and how it is changing every day. And this is something, of course, extremely impressive, comparing your own home country, but also comparing, say, Europe with America, with China, with Saudi Arabia, with Africa. And you can really clearly see where the pollution is highest, as it is expressed here through these satellite images. These images, as I said, we are getting updates every single day. We have global coverage every single day, and you get this measurement every day. The only exception or the only caveat, it needs to be cloud-free, because this technology only works if there is no clouds. But if you don't get an image today, you may get one tomorrow or the day after tomorrow, but you really get very frequent, regular updates. And this is the best atmospheric trace house gas instrument in the world at the moment in terms of accuracy and observation frequency. This is an example of where this is used for Copernicus on a more routine basis. There are some of these elements flowing in now to show some of example applications. Climate change is obviously a very typical one, but also emergency management, floods, security. This is a refugee camp which is monitored using the satellite images, obviously very important for migration. So the European Commission has installed some big centers or big services, which are listed here, 6 of them, which are using our data in order to convert them into information as required for a number of applications. Another example, wildfires. This is something that obviously is threatening life of people and causing huge damages. And again, the use of satellites is very important to detect where these fires are. But also, once the fire has occurred, as you see here, you can map which area has been damaged and how much the damage is. You can measure how much agriculture, how much forest, how many houses have been burned and have been damaged. And this is, of course, very important also for cleanup operations, for insurance companies and similar institutions. Climate change is a big topic with which we work and where we measure, where we have different measurements. This is an example of some of these measurements we are taking, but there are many, many more. Sea level rise, for example, the sea level is increasing, as we know. It will be increasing by more than 1 meter, maybe 1.3, 1.5 meters by the end of this century. That means everything that on average will be 1.5 meter higher because of climate warming. Ice sheets, as you know, are melting. Ocean salinity is measured, lakes are regularly monitored, glaciers and permafrost is measured. So there's a number of climate parameters which we are measuring, which all are part of the overall system in order to really have a full understanding of how the planet functions. This is one example of ice melting, again measured from our Sentinels, our Sentinel-1. What you see here is Antarctica, and you see the movie is playing the areas and how the melting is working and how this is, voila, here it is coming. So here, you see here the changes of the ice sheet thickness in meters, not centimeters, meters over the years from 1995 to 2015. And you will see some curves which are coming up now, if the video is playing, which shows you the change of this ice sheet. It seems to be not working. Okay, there should be some curves coming up, but I think it is somehow stuck, which are showing what the melting is bringing. But this slide here summarizes the melting, the ratio of melting. And you see here that in the West Antarctic, in the 90s, there was about 53 gigatons of, billions of tons of ice lost per year. And this number increased to 159, so a factor of 3. Also in the Antarctic Peninsula, there was also a very strong increase, but the values are much smaller. And this has been, for the first time, really measured with our satellites on a routine basis. It was quite an interesting scientific publication, which was published last year in Nature, which was cumulatively using all existing information to see how much this ice volume is melting in the Antarctic. And the result of the melting is increased sea level. Here you see again from 93 to 2019, or 2018 in fact, the increase of the sea level. You have in the 90s a value of 3 millimeters per year, and in the after 2000, around 2010, 4.8 millimeter per year. So this shows it is not a linear increase, it is exponential. That means that the sea level rise will go up, and what is shown here, that in the next 80 years, that means by the year 2100, we expect about 1.3 meters of medium sea level rise globally, which is really quite drastic. This is the medium sea level rise. There are some areas where it is more, some areas where it is less. So you can imagine that the cities around the coastlines are really in danger in Europe and globally. And this is something that is, of course, a very important aspect. Let me now, what you have seen here is a few examples of various applications, just to give you a flavor of what parameters we are measuring. But let me now show you a few things on what are the mega trends in Earth observation in space and what we are really confronted with in terms of challenges. We have a few challenges, but here are 3 of the main ones summarized. Climate change obviously is the big one at global level, and this affects every single person because the climate changes, and we have to measure, we have to monitor how this changes. On the other side, you see on the technology side a very strong revolution and a very strong change of technology, especially with artificial intelligence, with machine learning, with new technologies, very fast processing, cloud-based processing, and this is something that is going extremely fast on the IT world, and we have to see how we benefit from this IT revolution in space. And then you have something that is the commercialization. I mentioned SpaceX, a commercial company that is building rockets which were in the past built by NASA or by ESA, and now commercial companies are entering the space domain. And also in Earth observation, this happens. Google, Amazon, SAP, all these companies are working very closely with our data because they are for free, and therefore they really want to make business, and they do make business with our data. What you see here is that we get more and more eyes in the sky. That means more and more satellites are being launched in order to observe our planet. This number 220 is the number of satellites that have been launched in the last 10 years, 2007 to 2018. And if you compare this with the next 5 years, it's double the number. So that means the the amount of satellites quadruples by a factor of 4, so a very strong increase of number of satellites and therefore number of observations from space of our planet. And this is a fact. This is satellites that are being launched, meaning that we have more and more information coming from space. And that's good news, because we can use this information in many aspects. However, using this data, I mentioned 150 terabytes per day before as a huge challenge of data. This means that we need to apply new methods. Artificial intelligence is one of them, with machine learning, new computing, reusable launchers, new data, blockchain, new investors. So it's really a domain which is changing very fast, and where we need to really see how this goes and how this works. This is one example, and you may not know what it is. It looks like Van Gogh, the starry skies, but there's on it. This may be strange, because Van Gogh died in 1889. So how can he paint a satellite? Because he had a lot of fantasy, but I think this would go too far. So who knows who was the painter of this picture? It was a computer. So we showed a computer Van Gogh's picture of the starry skies. We showed him a picture of a satellite, and we asked the computer, using artificial intelligence, to paint a picture of a satellite using the style or the technique of Van Gogh of 150 years ago. And this is the result of it, which is quite amazing. And this is something we are using in our space technology. This is happening. And this is what we're using in our space technology. And as you see, artificial intelligence is obviously used everywhere for gaming, playing chess, Jeopardy, Go, for painting. You have seen an example here, but also music, for driving, autonomous driving, for classification of images, fusion of data. So artificial intelligence goes everywhere, but also in our case, we are using it quite a lot. But let me show this example here, and this is quite new and not yet existing, but this is where we in space go with artificial intelligence. Okay, this is just to compare a bit the computers you had here, 1997. Stella. 1997, where the first time an IBM computer was winning against Kasparov, as you know, in playing chess. So the computer, Deep Blue, was winning, and this was quite a revolution. Now this same computing capacity, which you see here in this big mainframe, is in an iPhone, and it gets smaller and smaller. And these are small chips, which are really the size of half a centimeter by half a centimeter. And they are doing now artificial intelligence on board of these small chips. And they're getting smaller, and therefore use less and less energy, which of course for space is very important. So what we are doing, what we are trying to do, is we bring these chips on board a satellite. And this is has not happened before. This is the first time that we are doing this. And just to show you how fast this development goes, we have decided just before Christmas that we want to fly this particular chip from Movidius, which is an artificial intelligence chip on a satellite. So we have decided we do it before Christmas, and we will fly the satellite on the 4th of September. We will launch it on the 4th of September on a small satellite, because it's an experiment, but with an AI chip on board, and we do processing on board, and we let the satellite decide what images to take and which ones not to take based on some rules which we defined before. And this will be first, because it doesn't exist yet. It is an experiment for us. It may go wrong, I have to say that. But if it goes right, it shows the potential of AI, not only in autonomous cars, but also on satellites. And this is what we're doing. In our case, this little satellite, we call it BrainSat, or FESat-1, which has a brain on board. What it does is we ask it to distinguish cloud-free from cloud-covered areas and only monitor the cloud-free area, and therefore already save about 50% of data transmission, because on average about 50% of the Earth is cloud-covered. But you could also do other calculations. For example, count the number of ships in the Mediterranean, or whatever other application you train the satellite to do, or the chip to do, and this can be done. And this is quite revolutionary, and I'm very excited that this will be coming, and I hope this all goes well. If not, then I'd do another one a few months later, because this is something that I really believe is going extremely fast. And we are having, this is what we call the Phi lab. Phi, like the Greek letter Phi, is a lab which are introduced in Frascati in our establishment in Esrin. We have about 800 people working there. I'm the head of this establishment. But we created one building, which is called the Phi lab, which is an open space building. So it is literally open space. There's no walls, no office walls, but open space more in the mental sense that new ideas from outside should come in and really disruptive ideas where we test new technologies. And this Phi-Sat I showed before with the artificial intelligence is the product of this Phi lab, which was created there. And there we bring together nanosatellites, mega constellations, artificial intelligence, high altitude pseudo-satellites, so all type of ideas to really make sure that innovation drives our activities, and with innovation we stay on top of it and we keep having one of the best Earth observing systems in the world. And this is the idea of how we think that in the future satellites and other information systems are being networked. What you see here are our satellites. You remember the Earth Explorers I mentioned before, our science satellites. You remember the Sentinels, our operational satellites, or the meteorological satellites. So these are satellites which we are building and flying today. But we also want to connect with high altitude pseudo-satellites, which are flying in 22 kilometers height above the airplanes, but on a more constant basis. We call them hubs, or drones, or information on the ground through IoT, or small sat constellations where new constellations are coming up. And our vision is that all these measurements, they are not done individually one by one, but they are connected. And this is an integrated system of observations which is connecting all these various sensors in order to provide a weather forecast, an agricultural crop estimate, a fire warning system for the fireman, information for the farmer for his farm in order to use pesticides or fertilizers in the best possible way. So this is the way we are thinking this needs to be done and will develop. It's not yet existing, but this will develop in the future in order to develop Earth observation further. There's one slide here, and this, I don't want you to read the text, but just to say that all this, of course, needs investment, it needs money. And the way ESA is organized, I said at the beginning, we're having program proposals which we put to the table for ministers, and ministers decide, and they say, this is something I find interesting to fund, and therefore I put money on the table, and you have seen some of the examples before. So at the moment I'm putting program proposals together worth about 2.4 billion, and we'll offer it to ministers in November this year. We have a big ministerial conference for ESA, and I will ask them, I will say, look, this is what we can do. I want to do this in the future. Can you provide the money? Are you interested to co-invest in this program? Of course, I guarantee you that the money goes back to your industry, because this is the rule of ESA, that the money of a member state goes back to industry, but therefore we can do European programs of a large dimension, and this is what we are doing. And these are some of the themes which we are developing. I'm not going through them one by one, but just to say that in ESA we have to invest in innovation, because innovation is necessary to have the best observations from space for Earth observation, and therefore we are putting these proposals together. This will be my last slide, which shows one event that is upcoming. It happens to be in Italy. We call it the Living Planet Symposium, which you see here. It will be in Milan in 1 month's time. It is open for everyone. There's only a very small registration fee, I think of 50 euros or so, to cover some of the expenses around, but it's basically free. We expect 3,500 to 4,000 people. It will be the biggest space conference of ESA this year. It's the biggest one for Earth observation worldwide. And if you are interested in Earth observation, the use of Earth observation, then please feel free. We also organize events for school children, and my daughter will go there as well. We expect about 2,000 school children as well, in addition to 3,500 to 4,000 scientists and users of this space data. So please, if you're interested, feel free to come to organize yourself, and there's a website where you can log on and participate. And this was it, and I thank you very much for your attention.